And that work started with the fact that electric current flowing through a long straight wire produces a magnetic field that circulates around the wire. But how does the strength of the field depend on the distance from the wire? If a tiny segment of electric current could exist, it would produce a magnetic field proportional to the inverse square of the distance. The direction of the field is related to the direction of the current by the right-hand rule, or the vector cross product. The field would be biggest when the current segment and distance vector are perpendicular. But electric currents can never exist in tiny segments. So any real magnetic field must be found by adding up or integrating the contributions due to each segment of a flowing current. The field, due to current flowing in a long straight wire, is always perpendicular to the wire and decreases as the inverse first power of the distance from the wire. The net result is a field that goes in circles. The lines of force are circles concentric with the wire, and the field is the same all the way around each circle. On the other hand, if the wire is bent around into a loop, the current flowing through it produces what is known as a dipole field. A helical winding, or solenoid, is like a stack of current loops. It creates a field much like that of a bar magnet. If the solenoid is bent around into a circle, the donut it forms is called a toroid. The magnetic field of a toroid is contained completely inside the windings. There are no field lines outside. Therefore, since an electric current is nothing but moving electric charges, it follows then that flowing electric currents apply magnetic forces to each other. Currents flowing in the same direction attract each other, and currents flowing in opposite directions repel each other. The magnetic field as both similar to and different from the electric field. In an electric field, no work is done if a charge is moved around any closed path and back to its starting point. Therefore, when starting from any point on any path and returning to the same point, the change in electric potential is always zero. Therefore, the line integral of the electric field around any closed path is always zero. This is a fundamental property of electric fields.